In this section, we're looking at sequences and series. It's kind of a nice bit of a change from what we were working with all the different integration techniques. Integration will come up again, but we're going to take a little break and look at sequences and series before it does come up. So let's go ahead and define what a sequence is. Basically, we are familiar with a few sequences. There's a couple famous ones. One is the Fibonacci sequence. The Fibonacci sequence has two C's instead of two N's. Looks at the sequence of numbers. So it starts out 1, 1, and then it takes the sum of 1 and 1 is 2. Then it takes the sum of the previous two terms, 1 and 2 is 3, 2 and 3 is 5, 3 and 5 is 8, 8 and 5 is 13. These are the terms of the Fibonacci sequence. Now it goes on forever following this particular pattern. So each sequence kind of has its own set of rules. This takes the previous two terms to add to get to the next term. Now we also have other sequences that don't necessarily have particular names. For instance, we could have one like 1/2, 2/3, 3/4. If you can see the sequence here, I'm increasing by 1 in the numerator, and then in the denominator I'm also increasing by 1. So that would be something to notice. Another thing that you could notice here is the numerator is always 1 less than the denominator. So as this is going out, I could probably say if my denominator is n, my numerator is n minus 1. Now if we look at these terms, 1/2, 2/3, 4/5, it looks like to me as these terms go larger and larger, because they are getting larger, they're getting closer to 1. So they're increasing and they're getting closer and closer to 1. So we might say that it converges to 1. So although it will always get larger, it'll never go over 1. So it's converging toward 1. Now if you think about the idea of a limit, if you take the limit of this part of the expression right here, n minus 1 over n, as n goes toward infinity, that limit is 1. And we'll kind of tie that idea into this conversation shortly. We could also look at a sequence like 1/2, 1/3, 1/4, 1/5. The numerator is staying fixed. The denominator is getting larger and larger, so that means that this is getting smaller and smaller. So the terms are getting smaller. And although they constantly get smaller and smaller, they're not always going to go below 0, because these are positive numbers. So this is converging as well, but it's converging to 0. So when we talk about sequences, we're talking about basically these terms, and notice they're separated by commas, so I'm talking about these particular terms in the sequence. Let's look at another one. Let's look at 2 over 1, 3 over 2, 4 over 3. If you notice the pattern, 2, 3, 4, 5 in the numerator, the denominator 1, 2, 3, 4. We can see that this is getting larger. So this is 2. Actually, they're getting smaller. So this is 2, this is 1.5, 1.3 repeating, this is 1.2. So the terms here are getting smaller. And as these terms are getting smaller, they could be going toward a particular value, and in this particular case they are converging once again to 1. So each pattern kind of produces a bit of a different sequence, and then based on that sequence you get a different response. Let's go ahead and look at another one. Let's look at something like 2, 4, 6, 8, 10. Okay, this is definitely a sequence of even numbers, and it's diverging, meaning it's getting larger and larger. So basically we see here we have a sequence as any function. In this particular case, this is my function. Sometimes it's really easy to write the function that represents this particular value or produces this particular sequence. But it's this function that basically produces these terms. Now a sub 1 is called the first term of the sequence, and then as these go on, it's called the nth term of the sequence. And so basically I'd plug in n. So if I wanted to know the 50th term, I'd plug in the number 50 and it should give me the 50th term back out. Now usually these curly braces, a sub n, this would represent the sequence. So for instance, for this one up above, I could have n minus 1 over n. Now usually a sequence starts at n equals 0 or n equal 1. So we have to look at the problem or what's provided to us to see if it's starting out with 0 or 1. So the domain of a sequence is basically the set of integers, either starting with 0 or 1. Now sometimes it could start at 2 depending on the situation, but if that information is not given, you can usually go with 0 or 1. So let's look at some examples of some sequences and see what we can do with them. So for this sequence, we'll be given the function. So we'll be given a sub n, and in this particular case, a sub n is equal to n over n plus 1. Now usually you're given a start point, so I'm going to start us off at n greater than or equal to 1. So this means I start off at 1, and then I move up by 1s, because these are integer values that I'm looking at. So a sub 1 would be my first term. So that means everywhere that there's an n in this, I plug in a 1. So I'd have 1 over 1 plus 1. That would be 1 over 2. So there's the first term in my sequence. Let's look at a sub 2. So it'd be 2 over 2 plus 1. So that's 2 over 3. So there's the second term. A sub 3, 3 over 3 plus 1, which is 3/4. So this looks a little familiar maybe with something that we had on top that we were looking at. Now as I look at these terms, the numerator is always one value less than the denominator, or another way we could think about that up here is the denominator is always one more than the numerator. So we can see as these are increasing, they're getting closer and closer to 1, but not ever going over 1. So these continue on until a sub n is n over n plus 1, which was given to us. If we want to know whether these are converging or diverging, these terms, I could take the limit then as n approaches infinity of n over n plus 1, and I would get 1. Now why though? We need a reason why, so we need to justify this. These are my shortcut rules. This is true because the degree in the numerator equals the degree in the denominator. The implied exponent on both of these is a 1, and the implied coefficient is also a 1. So the ratio of the leading coefficients is 1 in this particular case. So these terms are getting closer and closer to 1. They'll never equal 1. But as my terms go out, they'll get larger and larger. So at some point I might have something like 999,999 over a million. Still not 1, but it's getting very, very, very close to 1. So that's kind of what's going on with this idea of a sequence. Now some sequences are recursive or recurrent, meaning it depends on the previous value to define the next value. So an example of this would be a sub n plus 1 is equal to negative 2 times n times a sub n. Now this sub n plus 1 is basically telling me about the term. Now let's go ahead and define this for values starting at 1, so 1, 2, 3 integer values only, and we'll also be given a start point here, a sub 1 equals 2. So for this example I just want to find some terms. Now for some of the homework problems you'll see in my math lab, you'll definitely need a calculator. If these problems were to show up on a test, there would be numbers small enough where you wouldn't need a calculator, that you could crunch them. If they show up on a handwritten homework, of course, you're welcome to use a calculator, but you need to justify all of your steps. So let's go ahead and start off with my first term, a sub 1. Notation is important here. They told us that a sub 1 was equal to 2. So that's an easy start. Let's go ahead and look at a sub 2. Okay, so a sub 2, that was a sub 1 plus 1. That's where the 2 came from. So that's negative 2 times n times a sub n. Okay, well let's figure out what a sub n was. What was n? Well, if 1 plus 1 is 2, and this, remember, was n plus 1, that tells me that for this term, n must equal 1. So here's n equal 1. So if we know n is equal to 1, I would just go ahead and plug 1 in here. And I also know negative 2 times 1 is negative 2. And I also know a sub n, and we know n is 1 in this particular case, so let me replace this with a 1, was given to me in my first term. A sub 1 was equal to 2. So 2 times 2 is negative 4. So a sub 2 is negative 4. Okay, let's go ahead and look at our next term. And we'll see a pattern here. So now we want to look at n equal 2. Now I have my start. So if n equals 2 for my next term, what I have here then is a sub 3, because 2 plus 1 is 3, equals negative 2 times 2 times a sub 2. So a sub 3 is negative 4 times a sub 2, but we know what a sub 2 is. It's negative 4. So I get a sub 3 equals 16. So you can see how this is building. I have to kind of go back to the previous term to find the current term. So let's look at n equal 3. So for n equal 3, I have a sub 4, because again, it's a to the n, or a sub n plus 1. So I'm kind of going after this idea right here. This is equal to negative 2 times 3 times a sub 3. So I'm going after this value of 3 to find a sub 4. So a sub 4 would equal negative 6, and then the negative 3 is right here. I kind of jump back, and then I can plug in my value for 16. So a sub 4 would equal negative 6 times 16, which is negative 96. And I could keep kind of just going on and creating these values. Now sometimes you can see a pattern here. You know, sometimes at the beginning you'll look at this and think, oh, okay, here's my first term. It's going from 2 to 4. So it's the sequence of even numbers. But yeah, I check a third term and you can see that's not happening. Another thing that you might see here is this is called an alternating sequence, because my terms are going 2, negative 4, 16, negative 96. So if we look at the terms, kind of put them in order, we had 2, negative 4, 16, negative 96. This is alternating. This pattern continues. That's what the dots mean, of course. This is called an alternating sequence. The reason it's called alternating is the signs are alternating between positive and negative in a predictable pattern. Now sometimes when you're looking at these, you can find a pattern, like I said, 2, 4 is even, but it doesn't work for the third term. This one's pretty interesting. 2 times 2 is 4. 4 times 4 is 16. So this was times 2. I'm not going to worry about the positive negative right now. This is times 4. 16, if we take 16 times 6, I believe we get 96. So if you had to guess, you would probably say, well, I'm multiplying by 2, 4, 6. This is probably by 8. And 96 times 8, that would be 700. Let's get even bigger. Yep, 768. 768, and it's going to be positive because my signs start positive, negative, positive, negative, positive. So some of these you can look at and kind of predict a pattern. Some of them are not so obvious though, and sometimes you can verbalize the pattern very easily, sometimes not. So this one just looks like we're multiplying by increasing even powers. So 2, 4, 6, 8. But I write it in recursive form to be able to plug in any value to find any term. Because if I said find the 50th term, this, knowing my pattern here of 2, 4, 6, 8 is not really going to help very much. But if I knew my 50th term, would be easy to plug in and find that. So that's an example of working with the sequence. Again, sometimes they're a lot easier to describe than they are to actually write a mathematical formula for, and sometimes more than one formula is possible to describe these. Now this particular sequence, my terms are getting larger and larger, and they're also alternating. So if we were to graph this, and this is not going to be a 100% accurate graph, but it'll be kind of close. These would be my terms for n equal 1, n equal 2, n equal 3, etc. So what happens here is for n equal 1, I think we're at 2, and for n equal 2, we were down here at negative 4, and n equal 3, we're at 16, I believe. Yeah, n equal 3 is 16. N equal 4, we're clear down here at negative 96. So you can see that these terms are going wider and wider and wider, alternating between below the x-axis and above the x-axis. So it's an alternating sequence, and this particular alternating sequence diverges. Not all alternating sequences will diverge. This one happens to. So when we're looking at sequences, it's important to be able to talk about whether the terms are converging or diverging, and then also to be able to talk about how to define the terms and how to find those terms. Now the next thing I want to look at are partial sums. Now partial sums are based on adding terms of a sequence. Now the reason we're doing this is if we can predict a partial sum, we can predict what the overall sum will be perhaps. And we can predict whether it will converge or diverge. So let's go ahead and consider an infinite series. Now this particular infinite series we know is infinite because it has an infinity sign involved. So a lot of times we'll use a subscript of k or I or j or n, but this infinite series is going to go from k equal 1 to infinity, 1 over k plus 8. Now what I'm doing, summation, this Greek letter sigma means to add. So if I were to write out this sum, it would look like for k equal 1, I'd have 1 over 1 plus 8. And then I would go plus because I'm summing these, and I have k equal 2, 1 over 2 plus 8. K equal 3, 1 over 3 plus 8. So you can see it's this term, this piece is the one that's increasing. Now this goes on forever because it goes out toward infinity. So you think, well, I'm adding these things together, so if I keep adding positive things, it's going to keep getting larger and larger. But as it turns out, they can keep getting larger and larger, but still converge toward a particular value. So what we can look at here are called partial sums to use to try and predict what's going to happen here. So let's go ahead and look at some partial sums. Now these partial sums we actually turn back into a sequence, so it's kind of interesting. We start with a sequence, we sum an infinite series, and then we look at the sequence of the partial sums created from that. So the first partial sum, s sub 1, is just the first term, 1 over 1 plus 8, which is 1/9. My second partial sum are my first two terms of the series added together. So we know from here 1 over 1 plus 8 is 1/9, 1 over 2 plus 8 is 1/10, and this would be 19 over 90 after we find our common denominator. So that's the second term. S sub 3 would be S sub 2 plus my next term. So we'll write it out here, but you'll basically get the idea. This is S sub 2, we already have that from up above, plus my third term of the partial sum. So this would be 3 plus 8. So you can see that this basically builds from the previous partial sum and I add the next term. So we already know from here we have 1/9 plus 1/10 plus 1/11. We know 1/9 plus 1/10 from above was 19 over 90 plus 1 over 11. And then we keep working toward finding our common denominator. In this particular case, it looks like we could go after 990. So 19 times 11, I'm going to find my common denominator by multiplying top and bottom by 11 here. 19 times 11 would end in a 9, so 299 plus 90 all over 90 times 11, which would be 990. So this would be equal to, if I add these together, 389, 299 plus 90. Actually, I wrote the answer here. I got to be careful. So top and bottom, 19 over 90, multiply top and bottom by 11. I'd have 209 over 90, multiply top and bottom by 90 here, and I'd have 299 over 990. And if you can reduce it, you should. 299 over 990 does not reduce, and so that would be S sub 3. And then we keep going through the same thing to find S sub 4. So what we have here is a sequence of partial sums. We have S1, S2, S3. And S1, if we look up above, was 1/9. So this goes 1/9. S2 was 19 over 90. S3 was 299 over 990. It's kind of interesting, the denominator just looks like I'm just including an extra 9, some sort of a pattern here, 990, 990. Will be interesting to see what the next one is. So this is my sequence of partial sums. So that's what the curly braces here mean, is the sequence of partial sums. And you can find those partial sums, and then based on the partial sums you can start to predict what's going to happen with the subsequent sums. So if I can predict what's happening with the nth sum, I can predict what's happening to this entire series. Now a lot of your calculators, you could plug this partial sum in right here. You have a summation key, and you could get an idea whether it converges or diverges immediately. But again, we need to be able to show that by hand as well. Okay, let's look at another example. Remember, some of these are recursive, meaning they're based on the previous terms. You just have to be careful about how you plug those in. And we can also talk about alternating sequences. So if we talk about alternating sequences, remember that means a positive, negative, positive, negative. If they're based on trig functions, sometimes they go positive, positive, negative, negative, because you know that relationship between sine and cosine as we take derivatives can change as well. So when you're writing these out, there's more than one way to try and come up with a formula that talks about what the sum is. So you have to be really careful when you're working with those. So a couple of things I want you to watch out for. A sub n just represents a term. I guess we could be more specific. The nth term of a sequence. S sub n represents the nth partial sum, which means I had to add things to get there. The nth partial sum of a sequence. And we should probably say series here, because series is when I'm adding up the terms. So be careful when you're working through your homeworks and in my math lab and on your handwritten homework and exams. Are you looking at a sub n, the actual term, or are you looking at s sub n, the sequence or the partial sum for that particular series? So let's go ahead and look at an example where we might be asked to actually write the function that produces a particular series. So let's start with k equal 1 to infinity. So this is an infinite series. This one is going to be 64 over 2k minus 1 times 2k plus 1. So when we start with this, I think it would be interesting if we want to find the terms of the sequence of partial sums that we need to start adding them up. So let's go ahead and look at the sequence of partial sums. So we'll start with s sub 1, and the reason that we'll start with s sub 1 is I have a 1 here. So s sub 1, what I'll do is I'll plug a 1 in, so I'll have 64 over 2 times 1 minus 1 times 2 times 1 plus 1. 2 times 1 minus 1, 2 minus 1 is 1, 2 times 1 is 2 plus 1 is 3, so I get 64 thirds here. So 64 thirds is s sub 1. S sub 2, then I would take s sub 1, which we just found out was 64 thirds, plus my next term, so this was s sub 1, plus I'm going to add my a sub 2 term. So I'm plugging in a 2 now. So when I plug in a 2, I'll have 64 over 2 times 2 minus 1 times 2 times 2 plus 1. So the 64 thirds I'm dragging along because I already know this value from over here up above. And then my next term I'll have 64 over 2 times 2 is 4 minus 1 is 3. 2 times 2 is 4 plus 1 is 5. So I'll have 64 thirds plus 64 over 15. I'm going to have to do some addition and subtraction here. So I'll multiply top and bottom by 5 here. So 64 times 5 is what we're going to have for my numerator here. 15 will be my denominator on both of these now. So 6 times 5 is 300, 4 times 5 is 20. So we have 320 here, plus my 64 from here, which equals 384 over 15. 15, I think this is going to be reducible as well. We get 384 over 15. I can divide top and bottom by 3 here. So I end up with 128, 15 divided by 3 is 5. So this means s sub 2 is equal to 128 over 5. So remember, s sub 1 was 64 thirds. That means the first term. S sub 2 means my first two terms added together. So let's go ahead and look at S sub 3. So that's going to be s sub 2 plus 64 over 2 times 3 minus 1, 2 times 3 plus 1. So s sub 1, remember, was just the first term. S sub 2 was the first two terms added together, so this was a1 plus a2. So now as we're working, I know s sub 2. S sub 2 was 128 over 5. So I have 128 over 5. Now if you want, you can write out the first three terms. Okay, or you can just, use your math from the last one. So this next one would be 64 over 2 times 3 is 6 minus 1 is 5. 2 times 3 is 6 plus 1 is 7. So finding a common denominator here, I can multiply top and bottom by 7. So s sub 3, remember we're looking at s sub 3 here, would be 128 times 7, which would be 896 over 35 plus 64 over 35. That'll give us a nice number. So it looks like it'll give us 1,960 over 35. Now both of these are divisible by 5. We can see that because they end in zeros and 5s. So 960 divided by 5 would be 192. 35 divided by 5 is 7. So there's my s sub 3. So you can see that as we're working through here, I should be able to start making some predictions. So let's go ahead and look at the sequence of partial sums that we've come up with. Now you may be asked to find the sixth partial sum, then you'd have to add up all those terms. But let's see what we have for now. So s sub 1 was 64 over 3. S sub 2 was 128 over 5. S sub 3 that we just found was 192 over 7. So I'm trying to figure out a pattern here, something I could predict. Well, one thing I see in the denominator is I have a sequence of odd numbers, 3, 5, 7, etc. So let's go ahead and put some indices on these. This is s sub 1, s sub 2, s sub 3. So I wonder if there's a relationship between this subscript 1 and this 3. Well, to produce a sequence of odd numbers, if we wanted even numbers, we could just take 2 times n. And of course, any n I plug in and multiply by 2, I'd get an even number. So for a sequence of odd numbers, I could try 2n minus 1, which would produce an odd number, or 2n plus 1, which also produces an odd number. So I think that we could do 2n, let's do minus 1 here, and let's see what happens. Now let's look at the numerator. 64, 128, that's doubled. But 128 doubled is 256, so that doesn't work. So I wonder about 64 times 3 here. So this is 64 times 2 is 128. 64 times 3 is 192. So it looks like to me I'm multiplying times 2 times 3. Kind of looks like my pattern here. So let's go ahead and write out a few other things first to try and clarify this. This is 64 times 1. This is 64 times 2. 64 times 3. And I would guess that if we had to produce our next term, it would be 64 times 4. Now let's look at our denominator. Remember, we thought this might be 2n minus 1. Well, this is where n equal 1, n equal 2, and n equal 3. And that subscript is coming from the partial sum indice. So if I put in a 2 times 1 minus 1, let's see what we get here. 2 times 1 is 2, 2 minus 1 is 1. I need a 3, so that didn't work. Let's change this to a plus sign. 2 times 1 is 2, 2 plus 1 is 3. It works. So let's try it down here. 2 times 3 is 6. Oh wait, I have to plug in a 2 here. 2 times 2 is 4 plus 1 is 5. That works. So these are just trial and error. You kind of try and go through and figure out what I can create here for a function that creates this particular sequence. 2 times 3 is 6 plus 1 is 7. So this works great. Now notice it's the 1, the 2, the 3 that are changing. So the formula that I could write here then looks like to be 64n over 2n plus 1. Now to me this looks like it will work great as long as we're starting with the number 1 for n. Now if I wanted to find the value of the infinite series, what I would do then is I would look at my function that I just wrote here, and I would say, okay, what's happening as n goes toward infinity? So I take the limit as n approaches infinity of this sequence producing function, and I will get 64 over 2, which is just 32. Now why? We have to have a reason, because the degree in the numerator equals the degree in the denominator, therefore the limit is the ratio of the leading coefficients. This only works when the degrees in the numerator and the denominator are the same. So this is an example of looking at those partial sums, and based on those partial sums being able to make a prediction about the pattern and then draw some sort of a conclusion about the infinite series. Now again, if you would have just plugged the infinite series in up here, that was a long time ago. Yep, 64 clear up here. Clear up here, the 64 over 2k minus 1, 2k plus 1. I don't know if I would have got 32 out of that. So that's why it's so important to be able to go through this process. You know, a calculator can pop it right out, but we need to be able to go through this process and write out these sequences and make these predictions. And once we see these patterns in the numbers, you'll start to see all sorts of things come out while you're working. Let's go ahead and look at another example to give you some practice with these. This next one is going to be another infinite series, so we'll start with an infinite series. And this infinite series will be k equal 1 to infinity. And let's do 2 over 3 to the k. So if I were to write this out, I'm going to do this one a little bit different so you can have a couple different strategies to look at. Really what this is 2 over 3 to the first, plus 2 over 3 to the second, plus 2 over 3 to the third, plus 2 over 3 to the fourth, plus 2 over 3 to the fifth. You kind of get the idea, and this would go out toward infinity, 2 over 3 to the infinity. Well, it looks like to me this 2 over 3 to the infinity, these terms are getting smaller and smaller, so 2/3, 2/9, 2/27. But I know the terms are getting smaller, but I'm kind of wondering what the sum is going toward though. So let's go ahead and look at the sequence of partial sums to see if we can predict that. Now the sequence of partial sums, I kind of already have this written out a little bit. S sub 1 is just 2/3 then. S sub 2 is 2/3 plus 2/9. It's just these first two would be S sub 2. And then S sub 3 would be 2/3 plus 2/9 plus 2 over 27. So these three would be S sub 3. And then S sub 4, 2/3 plus 2/9 plus 2/27 plus 2 over 3 to the fourth is 81. And so let's go ahead and find the values for these now. So 2/3, that's already simplified. So here I'll multiply top and bottom by 3, so I have 6 plus 2 over 9, so I have 8/9. So I'm already seeing something interesting. It looks like the denominator is always one more than the numerator. So far, that might change. So here I have my 2/3 plus 2/9. So that was, if we want to go back, 2/3 was 6/9 plus 2/9 plus 2/27. So we know that this was 8/9. I could have just written that down to start with. So this would be multiplying top and bottom by 3. 9 times 3 is 27. 8 times 3 is 24. So I get 26/27. So I like going through the math on these and not plugging and chugging with my calculator, because I start to see the patterns a little faster that way. After you start seeing these patterns, it makes things a lot easier. Well, I already know what these three numbers added together are from up above. It was 26 over 27, and I need to add 2 over 81. 27 times 3 is 81, so I'll multiply top and bottom by 3. 26 times 3, 25 times 3 is 75, so the 78 plus 2 over 81, so I get 80 over 81. So I definitely see a pattern here. So let's go ahead and write out these sequence of partial sums. So this is S2, This is S3. So S1, the sequence of partial sums. So we have 2/3, comma, we're not adding these up, I'm writing out those partial sum sequences, 80/81. So this first one was S sub 1, S sub 2, S sub 3. So we're trying to make a function, we're trying to write a function here. So I'm seeing a few things. First of all, this 3, this is 3 to the first. This next one, I'm going to write that down a little bit lower. So I'm going to put in my fraction for each one here. So this is 3 to the first. So I can predict that. 3 squared is my next one. And then, this is kind of interesting, made a big jump here. So this was 3 to the, whoops, I forgot to write one of these in here. I forgot S sub 3 right here. So let's get S sub 3 in here. That's 26/27. And then I have S sub 4, which was 80/81. This will make more sense. Now my powers of 3 will work. So this is 3 cubed is 27. And then my next one would be 3 to the 4th. So that kind of takes care of the denominator, 3, 9, 27, 81. But let's look at the numerator. Okay, so I notice it's always 1 less than the denominator. So if we look at this, this is always going to be 3 to the n, and the numerator will be 1 less. Now this minus 1 is not in the exponent. So I take 3 to the n and I subtract 1. So let's see if this works. 3 to the 1 minus 1. 3 to the 1 is 3, 3 minus 1 is 2, that gives me my 2/3, so that works. Let's look at 3 to the second minus 1. 3 squared is 9, 9 minus 1 is 8, so that works. So let's look at 3 cubed minus 1. That works as well. 3 to the 4th minus 1, that works too. So it looks like this would be 3 to the n, and now remember this minus 1 is not part of the exponent. The minus 1 is subtracting 1 from the power of 3 to the n. Now this only works for n greater than or equal to 1, meaning I'm starting at 1. So I think that the value of this infinite series looks like, to me, it's getting closer and closer to 1. So 80/81, eventually I'll have some very, very large number. The numerator will be 1 less than the denominator, so it'll get closer and closer to 1. Now in order to figure out what this is summing toward, I should take the limit. It looks like to me it's going toward 1, but we need to establish that somehow. So the value of the infinite series, I would take a limit of this. I would take the limit as n approaches infinity of 3 to the n minus 1 over 3 to the n. Now you might look at this and say, oh, the powers and the exponent are the same, but notice that only works, those shortcut rules only work if my exponents are integers, not if they're variables, which in this case they are. So if I take this limit, I get infinity over infinity, which is indeterminate L'Hopital's. So we're using L'Hopital's rule here. So indeterminate L'Hopital says I need to take the limit as n approaches infinity of the numerator, the derivative of the numerator, which is going to be 3 to the n natural log of 3 times u prime. So I'll write that formula off to the side. It's definitely one that you'll want to have on your formula card. So the derivative of n is 1. Let's do the same to and the derivative of 1 over here is 0. Derivative of constant is 0. So the derivative of 3 to the n is 3 to the n natural log of 3 times the derivative of n, which is 1. So then I can simplify and apply L'Hopital's again. So as n approaches infinity, everything cancels here and I'm just left with 1. So the limit of a constant is just a constant. So this means that the sequence, all of these terms, are getting closer and closer and closer to 1. And that's kind of what we predicted. Now the side note here. Note, the derivative that we were just talking about, the derivative with respect to x of a to the u is equal to a to the u natural log of a times u prime, or du dx if you want to think about it like that. So this is a good one to know in case you don't remember it. So that's how we got that derivative. So that's telling me that the series up here that we started with so long ago, if I actually wrote out all these terms and added them up forever and ever and ever, I'd get closer and closer to 1, but I'd never go over 1 because remember, this is the idea of a limit. Okay, let's go ahead and look at a last example. Sometimes we're going to be looking at some application problems so you can see where these are useful. Besides just being fun, they're very, very useful. So our application problem that we're going to look at asks us to think about radioactive decay. So let's go ahead and let m sub n be the mass of the radioactive material. At the end of the nth year. And we have to be given a little bit of information here. Given a material converts, let's say 60% of its mass to another element. Every year. And this is due to radioactive decay. So this is the idea of kind of like carbon dating. Okay, so let's think about this. Let's start with our initial amount. That's present, let's say, is m naught, because that's initial amount, n sub 0, n equals 0, is, let's do 25 grams. Okay, so if we know we're starting with 25 grams, so m naught equals 25. Well, I want to find out m1, m2, how much is left after m1, how much is left after m2. So I'm actually looking for these terms of a sequence. So I'm looking for some terms of the sequence. So m1 and then m2, m3, etc. So these are terms of the sequence. These are not partial sums. These are terms of a sequence. Okay, so the amount that I have beginning was 25 grams of radioactive material. Now it converts 60% of it to another element, so that means 40% is remaining. So that's what the part we need to be really careful of. So 60% converts, 40% remains, and we want to know how much is remaining at the end of the first year. So we have 40% here of the original amount. So I have 0.25 times 4, which is going to be 10 grams. So the end of the second year, again, 60% of this amount is converted, 40% remains, so I have 0.40 times 10, which is 4. At the end of the third year, I have 0.4 times 4, 4 times 4 is 16, move the decimal, 1.6. m sub 4 would be 0.4 times 1.6, 16 times 4 is 64, 2 decimal would be 0.64. At the end of the fifth year, we have 0.4, 0.64. 64 times 4 is 256. 3 decimal would be 0.256. You kind of get the idea that we have here. Now, a couple of things I want you to watch out for. In my math lab, a lot of times they'll ask you to round it to a particular value. So in this case, if they're asking us to round it to tenths, this would be 1.6, this would be 0.6, this would be 0.2. If they're asking us to round to hundredths, it would be 10, 4, 1.6, 0.64, 0.26. So make sure you're reading those directions about rounding. They will be important. So those are the amounts that are left after 5 years. Now, it looks like to me it's getting smaller and smaller, so I think this is converging to 0. So eventually, there'll always be a minuscule amount of the radioactive material there, but may not be measurable, but it is going towards 0, that idea of a limit. So what we want to do is we want to go ahead and find the recurrent relationship that generates the sequence. Now we know this one is recurrent, which means it relies on the previous estimate. So what we could say here then is the next term relies on the previous term. So what we're going to start off with here is m of n plus 1. So that's the next term. And what it does is it says that's 40% of the previous term, which is m sub n. And then, of course, we have to say, well, we started with 25, because we have to know our initial start value, otherwise we can't do these. So each of these relies on the previous term. So if we wanted to write these out a little bit differently, we could see that occurring. So this would be 0.4. All of these have this 0.4, so that kind of helps me define these. And then instead of putting in the number, let's put in the value. 25 was m naught. Okay, and then we took it times 10, but 10 was m1. So m naught, m1, m2, m3, m4. Now remember, this was m1, this was m2, this is the third term, the fourth term, and the fifth term of the sequence. So we can see that this is always one less than the current term I'm on. So this helps me find that value. Now, this particular one is not so easy in terms of finding the limit, because I look at this and I think, gosh, I really can't just plug in n goes toward infinity here and get a number, because I'm plugging in the previous term. So this one, we have to kind of look at this, and we could graph this and look to see what's happening. And then after we look to see what's happening, then we could try and predict what's going on. But graphing this one doesn't really make much sense. So I think what we need to do is to think about, could we write one single function that doesn't rely on the previous term to figure out what's going on here? So let's go ahead and look at the formula that we could try and write for this. Now everything on this that we've worked on hinges basically on 25. So it hinges on that start point. So let's go ahead and write these out one more time. So we have 25, then we have 10, 4, 1.6, 0.64, and 0.256. So let's see if we can write something out here. Definitely 0.4 is something to do with this. Also that has something to do with this is the start value of 25. So let's thinking about this start value of 25. And remember, this was when n equal 1, n equal 2, 3, 4, 5, etc. So I'm going to start with a 25, and then to get to my next term, what I did was I plugged in, multiplied by 0.4. So 25 times 0.4 gave me that value of 10. So that worked for this one. So 25, I'm going to write that underneath there. 25 times 0.4. And that was to the first power. Okay, so then I'd have 25 times 0.4. How did I get that? Well, I would have taken 25 times 0.4 times another 0.4, which would be squared. 0.4 times 0.4 is 0.16, 25. Yep, that works as well. Let's go ahead and look at our next term. So this next one would be 25 times 0.4 cubed, 25 times 0.4 to the fourth, 25 times 0.4 to the fifth. So if I look at my power cert, 5, 4, 3, 2, 1, this was 0. Well, that's interesting. So if I'm trying to figure out what's going on, it takes trial and error. There's no easy way to look at this and just automatically come up with it. It takes trial and error. So for this one, if you kind of don't see what's happening here, remember 0.4 to the 0 is 1, so I'm starting with 25. So for this next one, that one's pretty easy. But now I'm going to 25 times 0.4. So I'm starting with 10. And then I have to multiply that by another 40%. 0.4 times 0.4 is 0.4 squared. So that's how I can kind of start developing this, is to go ahead and write out the actual terms. So I think this looks pretty good. This is 25 times 0.4 to the n if n starts with 0. So n equals 0, 1, 2, 3, etc. Now this formula wouldn't work if I start off with n equal 1. So even though I have my n equal 1 up here, it looks like to me this starts better at 0, so I can just define that down here. Now if I don't like that, I could start this off with 25 times 0.4 to the n minus 1. So if n is 1, 1 minus 1 is 0, then this all washes out and looks pretty good here. So then I could start it with n equal 1, 2, 3. So it depends on my starting point for my formula. So one of the important things that you need to do is to always define the domain of how you're starting, n equals 0 or n equal 1. And sometimes that will be given to you, which will force you to write one of these particular formulas that produces that sequence. So what we have here is either one works depending on the domain. So you might be given a particular domain that has to work. So be careful, make sure you always read the instructions to figure out if there is a restriction on the domain. As usual, when you're working through these, please realize it's trial and error. You're not going to be able to instantly see all of these patterns. You have to write out some of these terms. That's why on these I really think it's a poor idea to use a calculator, because you don't see some of these patterns because you're not working with the kind of the foundation of these numbers first. If you have questions, please send me a screenshot. I'm happy to help. I'm also happy to set up online office hours. Just let me know what you need. Good luck.